Hi class, so what we're going to talk about is cyclogroups, right? And so cyclo just means in a ring, right? So when you see the term cyclo, it's just going to tell you that they're in a ring. Right? Now, we previously talked about conformations and talked about sterics and different types of strain, right? Remember, strain is anytime that it deviates from what it wants to be. So let's just do a quick review. If you have a carbon molecule that's not in a ring, so we have a carbon with 4 groups. Excuse my penmanship isn't the best today. We have our hydrogens. If you remember, it's going to have a tetrahedral shape. And then that tetrahedral shape is going to have a bond angle of 109.5. Right? And so that's what they want to be, right? And so that's where this number over here comes from. It says we're going to go from 109 to 60. And so 109 is what a carbon tetrahedral group would normally be. So it normally wants to be 109.5, right? And the reason it's going to be 60 in this group is that's the only way to make that triangle, right? So if we're going to make that triangle, that's going to have to be 60 degrees. Right? And so that strain of moving the difference from here is going to create angle strain. What I would put in your notes is the further you're away from that 109, the more angle strain you have, right? So the further the deviation is between the two, the more impactful that difference is going to be, right? So if the molecule has to be 107 instead of 109.5, probably not that big a deal. If you're going from 109 to 60, that's a big chunk, right? And so I think it highlights why there's this kind of idea that cyclopropanes don't form very well. And we'll actually talk about when they're in ethers in a cyclopropane, they're actually really reactive and tend to pop open because when you open them, you relieve that strain. The other thing that's working against this molecule is we've talked about things being eclipsed, right? Meaning that they're on the exact same plane. So if we look down this bond, these hydrogens would be stacked, these hydrogens would be stacked, same here, and then you could do the same in the back if you look down that back row. They don't like to be eclipsed. So if they don't like to be eclipsed, right, then that means this is a bad angle strain, right? And so, or sorry, not a bad angle, it is a bad angle strain for the cyclopropane, but you also have this bad torsional strain, right? And so they're stacking on top of each other. If they're in a ring, they can't rotate like a single bond can. They're kind of locked, right? And so it keeps them from rotating into that staggered conformation. So you have a couple of things that are going to create a high energy molecule. So that's why you don't see a ton of cyclopropanes. We can make them, and you will see them every now and then, but there's a lot of energy associated in making them. So it's a very high energy molecule. Like similarly, cyclobutane. So if you think about a square, right, we would think these would be about 90 degrees. Now, things want to be 109.5, right? That have a carbon group. They're trying to get to that tetrahedral. And so that's what they want to be. And so what this actually does is it makes this puckered conformation. So instead of being just flat, it moves this group up a little bit and moves this one down a little bit. Right? And it has a couple different things, right? It's going to pucker a little bit to reduce the angle strain, right? Because it makes this just a little bit wider. So not a lot, but a few degrees more. The other thing it does is it starts to set some of these hydrogens at least a little bit offset, right? So they're not going to be perfectly staggered, but at least they're not totally eclipsed, right? And so we can try to move a little bit. So as you can probably see, cyclobutane, still not great, but it's getting a little bit better, right? We're getting closer to that 109.5. I'd probably put a star by cyclopentane, and we'll actually do cyclohexane. These ones actually do form pretty readily, right? So they form on a pretty regular basis, and it's because now we're starting to get close enough, all right? So when we start looking at these groups, they've opened up enough where they're really close to 109. Okay? We can take this envelope shape. All right, and so what that does is I think you can see that this would be if it was just a cyclopentane, right? If it's drawn completely flat. You're going to have that same problem where all of these are eclipsed, and we've already talked about being eclipsed is a bad conformation. You'd rather be staggered. And so what we can do is move one of those groups up. And what that does is actually make this one staggered with these. right? It does help the bond angle a little bit, right? Because it gives us a little bit bigger range on those. And so it helps with two things. It helps with the angle strain, and then it actually makes all of these groups here staggered. It doesn't help with the ones on the other side, but these do get to be staggered. So it's, again, not perfect, but it's getting better, right? And it's actually good enough where you actually see a lot of 5-membered rings. So 5-membered rings and 6-membered rings are going to be the most common rings we see, and so they form really, really readily. All right, and energetically, the best molecule is cyclohexane. All right, because when we get to cyclohexane, we're actually at 109.5. So it's exactly what it would be in a straight linear chain. So we've gotten rid of that angle strain. And if you notice, we've actually drawn it kind of funny where it goes up, down, up. And so that actually makes our cyclohexane into what's called the chair conformation. And this chair conformation helps all the bond angles be 109. And it makes all of the carbons staggered from each other, right? Or all the adjacent hydrogens or whatever groups are coming off of the carbon staggered. So if you look at the ones right next to each other, this group, right, is going to be staggered. And if you look down this bond, it actually happens on every single one. And so it works really, really well. The other thing you can see, this is the side view. But if we look right down on top, you actually get a really good view that this hydrogen is pointing up. We actually skip a carbon where the other one's pointing down and then up. And so it goes down, up, down, up, down, up. And so it spreads them out as far as possible. Even the ones coming out to the side are kind of staggered, and they're not really shown well from the side one, but you can see it, or sorry, from the top view, but from the side one, you can see this is kind of pointing down while this is pointed up. And then this one's pointed down. So even those bigger groups off to the side are going to be pointed in different directions. One thing you should practice a little bit is making your chair conformations. So if we're going to make our chair conformations, one of the things that works really well is to draw kind of these slanted lines. And then you're just going to put like a little triangle on the end, pointing in the opposite direction. Okay. And then the way you're going to draw these is we're going to have groups pointing straight up and down, and we're going to have groups slanted. So the way I think about it, and we'll talk about these terms here on the next slide, but the axial ones always go straight up and down. And so if this carbon is kind of pointed up, then that axial will be up. This one's kind of pointed down, so it'll be down. This one's up, down, up, down. All right, so this would be all of my axial positions. Equatorial just are almost slanted. And the way I think about it is equatorial is like around the equator, right? The equator is right in the middle of the Earth. So these are going to go around the middle of the molecule. And so they're going to be slanted in the opposite direction. So the red one's pointing down, so this is slant up. That one's up, so it slants down. And it kind of just keeps going the opposite direction. Slants up, down, up. All right. And same here. So if we had those, let me just highlight these. So in this picture here in the middle, all of these in the middle are going to be my equatorial ones. Right. One kind of hidden there in the back. And then the ones pointing straight up and down are going to be my axial ones. These right there. All right. And so what you can kind of see is you get this nice little plane on top of my axials and my planes on the bottom of the axials. Same thing here. Let's do one more. All of these pointing straight up are my axials, and then all of these around the outside are my equatorials. And you're actually might be asking, well, where are the other 3 axials? They're actually right behind, and they're kind of hard to see, but I think there's just a little bit of them kind of poking out on the sides there, but they'd be pointing straight down. All right, so if it's just cyclohexane, so there's no methyl groups or anything coming off of it, you're going to have 6 equatorial, 6 axial. And remember, your equatorial are the ones on the side, right? So they're on the side of the molecule, so they're highlighted here in red. So these are my equatorial ones. These groups on top are going to be my axial, right? So axial is always going to point straight up and down. Equatorial is always going to point out from the molecule, right? And just kind of some different conformations looking at it so we can see how they spread out, right? But this top view, again, really highlights how those equatorials are kind of pushed out to there, and then the axials are coming straight up and down. And so the whole thought is this is trying to spread those groups out. And so we talked about conformations, right, where the molecule can spin. When you're in a ring, you're kind of locked, so you can't really get that same spinning. But what we can do, and what we actually get from these groups, is we get these chair flips. So that top one is going to pull down, and this one's going to pull up. So it's almost like an umbrella, right? If anyone's ever had an umbrella and it gets caught in the wind, or at least you've seen it in a movie, and the umbrella flips over, same thing's going to happen here. And what happens is each one of these bonds gets switched, right? So all these CH bonds that were equatorial become axial, right? So if you see all of these hydrogens here that are in this baby blue, this teal, are axial on top, and these are also axial. When you do this chair flip, this carbon's going to point down. So see how it's pointed down here, and it's going to pull this down with it. And all of these axial groups now become equatorial. So everything that was axial becomes equatorial, and everything that was equatorial becomes axial. And these two chair just kind of flip back and forth, back and forth. So if they're in solution, this molecule will constantly keep changing shape back and forth from the two. Right? So the groups go up and down from axial, equatorial, and they all flip at once. So everything that was axial becomes equatorial. Everything that was equatorial becomes axial. Now, where this is going to be important, we're going to talk about this here in a second, is just like when we did the conformations, we also want to put the two biggest groups further away from each other. What you should put in your notes is you always want the biggest group, right? So we have a choice between axial and equatorial. We always want the biggest group in the equatorial position, right? So in this case, they're all hydrogens, so it doesn't matter, but we're actually going to see here in a second that if we have a bigger group, the molecule can have a chance either being axial or equatorial. We're going to see that we always want that bigger group in the equatorial position. So this is why it matters. So this is exactly what I'm talking about. So if we assume that all these other groups are hydrogens coming off of it, and we have one methyl group, right? So cyclohexane with one methyl group. This methyl group, remember, if it's slanted, this is in the equatorial position. And if it's pointing straight up and down, it's in the axial position. All right, and I'll just kind of highlight that. So this is in my equatorial position, and this one's in my axial. You always want the bigger group to be equatorial. And just like the conformations, when we went from staggered to eclipse, there's some amount of energy to pay to putting it in that axial position. And so they'll keep flipping back and forth, back and forth. All right, if you're ever asked which is the most stable conformation, which one's the preferred conformation, which is the energetically more favorable one, it's always having the bigger group in the equatorial position. All right, so you're always going to want that bigger group in the equatorial position. All right. And so what you should just associate is I'm always going to find how to put the, excuse me, sorry about that. You're always going to want to put that biggest group in the equatorial position. All right, last thing, we'll kind of wrap this up, is if you have isomers, we can have a couple different ones, right? And we talked about constitution isomers, or groups that are made up of the same molecular formula but connected different. Stereoisomers tend to have the different shape, right? So we can think about like R and S. Right? If we had a double bond, we could have cis or trans. We can also do the same for cyclo groups. Let me show you what I mean. So we have our cyclo groups here. And if they're stereoisomers, they're going to have the same shape but different connectivity. Right? So if they're cis and trans, they're going to point in opposite directions. Right? And here's a really good example. All right, so if they're in a straight chain, it's not as big a deal because it rotates around like we saw with the propellers. But if they're in a molecule and they're kind of stuck on one side versus the other, okay, then that's going to tell you that this is going to be dashed, this is wedged. So they're pointing in the opposite direction. All right, so they're going opposite each other. So those are going to be trans. If they're pointing in the same direction, they're going to be cis. And it doesn't matter which one's wedged, which one's dashed. Just if they're opposite, they're trans. If they're both wedged or both dashed, then they're cis. Now, when you're looking at these structures, when you're drawing a chair conformation, and this is where it tends to throw people off, is if they're trans, it's just talking about the direction, not necessarily one's axial, one's equatorial. All right. So when you're talking about trans, it doesn't matter in terms of axial and equatorial. It just matters what direction. So if you notice, this one's kind of pointing up. Right? There's that slanted upness to it. So it's kind of slanted up, and the axial will be pointing down. This one's slanted down. And since they're pointing in different directions, that's why they're trans. This one, this group is pointing down, and this group is pointing down. And I know it's just slightly, like it's slanted pointing down, but they're still pointing down. So that's why they're cis. Right? And the difference between this one's still in the equatorial position, this one's in the axial, but they're still cis. Right? So cis just refers to the direction, not necessarily if they're pointing up or down. All right. So, or sorry, not necessarily if they're, it only matters about the direction, not the axial equatorial. Right? The axial equatorial will just kind of work itself out when you draw the molecule because they got a pointing opposite directions. All right, so let's try one. So let's do this together and we'll kind of tie everything together. And so if we're going to look at this, let's draw our chair conformation. Let's put a wedge with our methyl group on top and a dash with our CH3. So we have these two. Now, when we do this, we're going to assume that our methyl groups are drawn, and don't forget for our zigzag, everything else is just assumed to be a hydrogen. Right? So let's draw our pair conformation. So remember, we said there's two of them, they flip. It doesn't matter where you start, but we're going to draw something that looks like these two. So let's start up here. So there's our chair conformation. Now, let's just go ahead and put in our axial. So remember, our axial positions just point straight down if the carbon's kind of pointed down, and our equatorial slanted in the opposite direction. So this is pointed down, so our axial's down, up, up, down, down, up. And then our equatorial, and I'll put those in green, go in the opposite direction. So I think here in the end, it's easy to start. So it's going to slant down, up, down, up, down, up. All right, so everything in green is my equatorial. All right, now what we want to do is put our methyl groups in. And it actually doesn't matter where you start. You just want to be consistent. So we know these are going to be right next to each other. So if we kind of number around the ring, I like to start on the ends because I think it's easier to see. It really doesn't matter, but let's start on the end. So this is going to be carbon 1, 2. But once you number, you got to keep going around the ring. So 5 and then 6. All right, so you're just going to go around the ring. The other thing doesn't matter is wedge and dash, you're just going to kind of pick them going a direction, and then you got to stick to that. So let's say that everything wedged is going up. All right, so we'll draw my CH3 going up. Now, if we said wedge means going up, then dashed has to go in the opposite direction. So if we said that wedged is up, then dashed has to be up or down. We said it's the opposite, right? Because these are cis to each other, or sorry, trans to each other. So if wedge is up, dash has to be down. So here, we're not going to say, well, the other one's axial, so this has to be equatorial. We just care about the direction it's pointing in. So this one, the direction is down. So it's CH3. All right, and so this highlights that even though this is trans, in this case, they happen to both be axial, but it's the direction that we care about. This is pointing up and this one's down. Now, so this is one chair conformation. Now we want to draw the other one. And so the way this works is we're going to take this carbon and pull it down, and we're going to take this carbon and pull it up. All right, so what we'll do now is we'll draw our slanted lines the opposite direction. This group will point down, and this points up. All right, so this carbon here was this one. All right, so now everything still points the same direction, right? But now my axial up, down, up, down. Remember, my axials always point straight up and down, and my equatorials always slant the opposite direction. Okay. Now, this is the trick to it. This carbon here in orange has become this carbon. And the one that was down here went up, and so now it's up here. All right, so this is carbon 1. And things are going to still point the same direction. So we're going to say wedge is up. So now this is my up position. And so my CH3 goes there. All right, but in this case, now it's moved to equatorial. And we see that when we do a chair flip, everything switches. All right, so it's pushed up. Now, this went 1, 2. The 2 carbon has moved over. We're still going in a circle, so we got to count the same way. So we went 1, 2, 3, 4, 5, 6. So we're going to do the same thing, 1, 2, 3, 4, 5, 6. So then on this next carbon over, we said that if you're dashed, you're pointed down. In this case, the equatorial. So now we have the 2 chair conformations. And one of the questions I would ask you is, which of these is the lower energy conformation? Remember, having the bigger group equatorial is always better. And so if you're looking at these 2, both of these are axial, both of these are equatorial. And so if you have to choose between 2 groups, you want to put the bigger one equatorial. If you have the option to have a molecule where everything is equatorial, all the big groups, the non-hydrogens, perfect. So this gets to be my lower energy conformation. All right, so make sure you spend a little time thinking about this, that you're going to have your ring, and then you're going to relate the position to them, whether they're axial or equatorial. Okay. Last thing, when we talk about physical properties, right, we want to look at alkanes, and alkanes are typically insoluble in water. All right, so kind of tragically, if you see an oil spill, right, the oil spill just sits on top of the ocean and the water underneath, right? So the fact that they layer has to do with their density. So alkanes tend to have a lower density than water, but they're insoluble, so they don't mix. Same thing if you cook, right? Oil and water don't really mix, and people kind of use that analogy forever. The other 2 trends is the longer the chain, the higher the boiling point, right? So the longer that carbon chain, the higher the boiling point keeps getting. Okay? The other one is the more branching, the lower the boiling point. And what branching just means is if you have a straight chain, there's no branching. If you start to put a group in the middle, then that's branching, right? So branching means when you start to have those substituents, right? The groups coming off of it. So if it's a nice linear chain, there's no branching. Every time we start to put groups that are going to make it bulky instead of linear, it's branching. And so branching is going to decrease the boiling point. And while the longer the alkyl chain, the higher the boiling point. All right, so I hope this was